All right, let's jump straight in. Today, we're exploring how abstract math concepts actually translate into real-world strategic mastery. We're pulling our insights straight from the Cambridge 0580 syllabus, looking specifically at investigations, physical modeling, and using ICT tools. Because, let's be honest, mathematicians don't just sit around solving equations all day. They're actually decoding the universe. So let's get into it. Here's exactly what we're covering today. First, investigating mathematical patterns. 2, the house of cards. 3, the checkerboard puzzle. 4, modeling skydiver freefall. And finally, number 5, solving with ICT graphs. Okay, part 1, investigating mathematical patterns. Let's start with a classic, the house of cards. You know, deep mathematical understanding almost always starts in the exact same place. We analyze a simple, tangible pattern before we try to scale it up to infinity. Think about building a house of cards. If you build a basic 3-layer house, you can literally just count the cards by hand. It takes exactly 15. But what if we want to calculate the exact materials needed to build the world record house? We're talking an astonishing 61 layers high. We definitely can't sit there and draw out 61 layers by hand. We need a real strategy. And here is that strategy. The general overarching formula is this. C equals 1/2 n multiplied by 3n plus 1. In this little equation, C stands for the total number of cards, and n is our number of layers. By generalizing the pattern like this, we instantly unlock the ability to solve for a 10-layer house, or that massive 61-layer world record house, without physically stacking a single card. Honestly, algebra is basically the ultimate shortcut. Moving right along to part 3, the checkered board puzzle. So, let's shift our thinking from triangular layers over to grid-based geometry. Picture a standard chessboard. It's an 8x8 grid, right? That's 64 total squares, and it's perfectly symmetrical with 32 black and 32 white squares. But what happens when we start looking at rectangular boards? Let's say a board with 21 total squares. Suddenly, we've got 10 black squares and 11 white squares. That perfect symmetry is completely gone, which means we have to dig a bit deeper to find the underlying rules for any dimension. The key here is how we actually set up the rules for our investigation. To mathematically figure out the exact number of black and white squares on any m by n board, consistency is absolutely crucial. So we start by always keeping the bottom right-hand square the same color. From there, we just analyze the total area. If the total number of squares is an even number, well, the split of black and white is perfectly equal. But if the total is an odd number, like our 21 square example, one color is always going to have exactly one more square than the other. Make sense? All right, let's look at part 4, modeling skydiver freefall. Now we're stepping out of the puzzle world and into the high-stakes realm of physical modeling. Just take a look at this raw data tracking a skydiver's distance fallen over the very first 4 seconds of freefall. At 1 second, she's fallen 4.6 meters. But by 4 seconds, she's fallen 77.8 meters. The distance is compounding incredibly fast. Obviously, this is not a linear pattern. She is accelerating toward the ground. And this is a brilliant example of how mathematicians handle messy, real-world data. We strongly suspect there's a hidden equation driving this. Specifically, we think distance equals 1/2 k times time squared. Now, to actually prove this, we don't just plot time against distance. No, we plot time squared against distance. If our hunch is right, graphing it this way will give us a perfectly straight line, which makes it super easy to calculate that unknown constant k. So when we actually crunch the numbers from that data table, we find out that the constant k is right around 9.8. Now, if you've studied even a little bit of physics, that number probably just jumped right out at you. It's the acceleration due to gravity on Earth, 9.8 meters per second squared. It's amazing because our abstract mathematical model just perfectly aligned with a hard, undeniable law of physics. But here's the catch with modeling reality. You have to account for all of reality. A skydiver's speed doesn't just keep increasing forever. Eventually, the upward push of air resistance completely matches the downward pull of gravity. She's going to hit a natural speed limit, which we call terminal velocity. For a skydiver, that's roughly 195 kilometers per hour. So to make our model truly accurate, we have to pinpoint exactly when she hits that limit. And it's a step-by-step process. First up, we convert that 195 kilometers per hour into meters per second, just so it matches our other data. Then, using the velocity formula, v squared equals 2 times k times d, we calculate the exact distance she drops before reaching that max speed. And once we know the distance and the speed, boom, we know the time. This is absolutely critical. Think about it. If we want to predict her total distance fallen at, say, the 10-second mark, we have to know if she hit terminal velocity before those 10 seconds were up. If she did, that earlier gravity formula we used is useless, and we have to adjust our prediction. Finally, let's wrap up with Section 5, Solving with ICT Graphs. So what happens when our models and our equations get just way too complicated for mental arithmetic? Take a look at these sets of simultaneous inequalities. Trying to juggle the boundaries of 3 intersecting rules in your head all at once? Yeah, that's incredibly tough. And that's where graphing packages step in to totally save the day. There's a really brilliant technique here. We graph all the boundary lines, but instead of shading what we want, we shade the regions we don't want. By doing that, the simultaneous solution, the one specific area that satisfies every single rule, is left completely unshaded. It just isolates the right answer right in front of your eyes. Let's look at one more scenario where technology is a lifesaver. Check out these exponential equations, like 4 to the power of x equals 40. Well, we know 4 squared is 16, and 4 cubed is 64, so x has to be some messy, complex decimal somewhere between 2 and 3. This goes way beyond the simple rules of indices we can do by hand. The Cambridge material gives us a very direct instruction here. Just use a graphic display calculator. By plotting these complex exponential functions as visual graphs, we can effortlessly find the exact spot where the lines intersect with our target numbers. The digital tool literally turns a massive algebraic headache into a simple visual dot on your screen. And really, that's the ultimate takeaway from all these investigations. Whether you're figuring out the algebra for 61 layers of playing cards, tracking the exact gravitational pull on a falling skydiver, or using digital tools to isolate a solution space, math is a strategic toolkit. So I'll leave you with this final thought. When the problems in your own life or career get way too complex for simple mental math, how will you build the right model to find the answer? Thanks so much for exploring this with me today. And hey, keep looking for those patterns.